keep up the development. C# and .NET did, on the other hand, add new desirable features, but really kind of in a small way. And so people were unhappy about Java because it lacked certain features that should be easy to do and that aren't easy to do. If you've ever done GUI programming in plain Java, it's kind of a pain. You have to write all these event handlers. It's very verbose. And that fact that it's so verbose is something that people don't like. They say, you just write lots and lots of long, boring sequences of code to express very simple things. Java deals poorly with parallelism. And that's something that's more important all the time. And I'll talk about that a little bit later. Then when people particularly do big iron development like server-side programming, they end up writing not just Java, but a whole bunch of XML to do configuration stuff. And that's also very verbose, and then there can be mismatches between them. And they've not been very, very happy about that. And a few years ago, people who really were not happy doing web programming in Java noticed this new kid on the block called Ruby on Rails that just blew Java away in terms of productivity. So Ruby is very dynamic, and that dynamic nature makes it easy to do what's called convention over configuration, where you write much less in terms of code, in terms of artifacts, and the system can kind of figure out what it is that it needs to generate for you. Java lacks these dynamic abilities. So programmers are definitely getting restless. And you can see them getting restless if you look at a typical developer site, like I like to look at dzone. Go to dzone.com and check out what programming languages they're talking about on a given day. And you're going to see JavaScript, of course, Perl, Python, PHP, Ruby, Groovy, a little bit of Erlang, and maybe once a month there's something on exotic things like Fortress or Clojure. You may have heard of Dart, which is a new language that Google is trying to push. And then there are various very new creations that like Kotlin and Ceylon that may or may not ever go anywhere. So people are really restless. They're creating all of these new languages because they're unhappy with where the mainstream languages are going. And then, of course, there's Scala, the language that I'll be talking about today. So Scala was started in 2001, quite a bit earlier than some of the more modern languages on the previous slide, at the École Polytechnique in Lausanne by this fellow Martin Odersky. And he had this insight that I'll talk about in the next few slides, that if you fuse together the best of an object-oriented language and a functional language, that's actually a very powerful combination. And from the outset, he designed the language so that you can start with things that are very simple and grow to the largest programming projects and stay within the same language. And that's, of course, very useful because right now there are many projects that use a bit of JavaScript here, a bit of just some shell language somewhere else, and Java for the backend, and some domain-specific languages maybe for the database connection. So what he wanted to be possible to embed those domain-specific languages inside Scala, and we'll see a little bit about that. Now, Scala compiles to the Java virtual machine, so any Scala program that you write can call any of the millions and millions of Java libraries that are out there, and you can also call the other way if you're a little careful, and it also can compile to the .NET virtual machine on a good day. So that port has been a little bit neglected, but there was a time when people feared that, who knows what Oracle is going to do with the Java virtual machine, and it's kind of good insurance to have that in the background. So it's been quite successful in a number of big iron projects. Twitter, for example, runs the entire backend with software that's written in Scala, and I've never used the full thing, but I hear it's great. So I just can't express my thoughts in 160 characters. 100, okay, even worse. And now there's a bit of a commercial uptick. The folks from that university have founded a company called Typesafe.com that is hiring. There's actually lots of jobs in Scala. That is trying to get it more from a university project into something that's commercial. So let's just have a quick look at basic syntax so that we get a feel for what it does. And then I'll give a couple of use cases. But you'll need the syntax to understand the use cases. So it has type inference. In C++ and in Java, you always have to declare the type of a variable. And it's kind of silly because if you look at here where I'm declaring pi as 3.14, well, 3.14 is a double, so obviously pi must also be a double, so why worry declaring it? It's a strongly typed language, so you can't take pi and put a string into it now, but you don't have to declare its type. It's smart enough to figure it out. Semicolons are optional, like in JavaScript. Some people like it, some people don't. If you don't, you just stick them in. Syntax for functions is a little bit different than in Java. You always have the name first, and then you have the type afterwards. Whereas in Java and in C and C++, you always have the type first, and then you have the name. And I guess in Java it doesn't much matter, but in C, if you have complicated declarations, you know that that's a truly wretched convention. So these guys do it just like in the algol style languages. There are no primitive types, so you don't have to worry about the distinction between primitives and objects. In Scala, int is a class, double is a class, numbers are objects. The result type of a function is also inferred. So over here I have a function that multiplies a double by itself. So that's a double, and you don't have to say that area returns a double. It figures it out. Except for recursive functions where it's not powerful enough to do it. So here I have a factorial function, and it just computes factorial here. And I do have to say it returns an integer. It can't figure out by itself. Everything in Scala is an expression. So, for example, if else has a value, and the value it has is either the value of the if clause or the value of the else clause. So you don't have that distinction between expressions and statements that you might have in Java. In that case, it's very much like a C or any of those functional languages. So let's just have a concrete example here. First, no primitive types. So there is a method called to that works on integers. You say 1.to of 10, and it calls the to method on the object 1, integers are objects, and it returns a range. So here it returns the range of numbers from 1 to 10. And now we'll come to one of the powerful features, the powerful functional features. So the map method. So I'm going to take 1 to 10, which is that range of numbers 1 to 10. I'm going to call the map method on that, and I'm going to give it as its parameter a function, here the factorial function. So the input is the range 1 to 10, and the output is 1 to 10, each of them hit with the factorial function. So it's 1, 2, 6, 24, 120, and so on, if you remember your factorials. So that's nice because it means you can take a bunch of values and you can transform that whole sequence in one fell swoop. You'll see an example on the next slide. So when doing that, one often uses anonymous functions. There's a bit of a shortcut if you have a short function, and one often has these very short functions in this manipulation. You can just write the function in this form. Here I'm looking at the function that maps x to 1 over x. And I don't have to say def inverse equals the function that maps x. I just say the thing that maps x to 1 over x like that. And when I apply that in the map, then I get 1, a half, a third, and so on. In fact, I can do better than that. If the function if the parameter of the function is used exactly once, then I can write it as an underscore. So the manly thing to do is to write 1 over underscore, and then that way it takes that function, the inverse function, and applies it to all of the elements. Short and sweet. So that kind of thing makes the code more concise. If for whatever reason you wanted to have all inverses from 1 to 10, imagine how you'd have to do it in Java. You'd have to have a loop. You'd have to collect the answer somewhere. It's all just a few keystrokes. So why do you care? So let me give you a typical example. This was something that I assigned in the freshman programming course just a couple of weeks ago. So the faculty unions sent us this list of like 30 or so campuses, together with how much money the presidents of each of those campuses make. So here, for example, Horace Mitchell makes $285,000 a year. Not just that, he also gets $50,000 for housing allowance because the poor fellow doesn't have a presidential mansion, and he gets $12,000 for his car because, God forbid, otherwise he'd have to walk on foot. So we have this list in a file for everyone. And so what I asked them to do was to read in this file and to tell me what is the total of all of the salaries. And I just wanted all the salaries, not the housing allowances and all of that stuff. And of course they did it in Java, and it was, a kind of reasonably big Java program. So I'll show you how one tackles something like this in Scala. there is a call source from file just makes an object that can deal with files. And then you call get lines on it, then it gets an iterator through all of the lines, and oops, then I turn it into an array by calling to array. At this point, I have an array of lines. Each of them is just one string. So the first element in that array is this string. Oops, just the top one. The second one is this string, and so on. So that, of course, takes a bit of doing in Java as well. It's nice to have a one-liner for this. But so what? I didn't want to have an array of strings. I wanted to have the total of these fields here. Okay, which are those fields? They are the third one from the back. So now I have to take each of the strings and split them into individual pieces along space boundaries. Now, in Java, there's a method for that. If you have a string and you call string.split, and you give this regular expression, then it splits it on white space. So now each of the strings has been broken up into an array of strings separated by white space. Now notice that I can call a Java function from Scala, which is nice. I don't have to learn a whole new API. And also notice the nifty underscore dot here, which means just on the parameter call split. So now I have an array of arrays, which actually sounds kind of scary, except if you don't think about it. So let's not. And what do I want to do with each of those arrays? Well, for each of these arrays, so if I call the array W, I want to take the third thing from the back. So I compute the length, -3, that's the third thing, and now I access the array at that. For reasons you don't want to know, array indexes use round parentheses, not the brackets in Scala. That way you can't hurt yourself on the corners. So now we're actually pretty close. The result of this operation, it's a bulk operation, right? On all of the lines, I've picked out these numbers here. And now I have an array of these things. And in fact, I'm very close. Because now what I have to do, I have to take each of these strings, and I want to replace everything that's not a number with an empty string. That's the call here. That's, again, just Java API. That's still a string, so I call toInt on it. And then I sum them all up. And that's my answer. Now, I'm going to show you in a minute how it all fits together. The thing that makes this work is that you don't think of your input as being an itty-bitty thing at a time. You just think of, you now have this data set as an array, one line at a time, and now you want to operate on each of the elements in that array, and you want to do all of these operations together. So the programming style that you develop is that you say, I have a collection of stuff. It's not quite what I want. I don't want all that stuff. I just want the third thing from the back. Let me just apply that filter. Oh, but now I still have a string and not a number. I can't convert it to a number quite yet because of commas and dollar signs, so I need to hit it with something that replaces them. And that's the thing over here. And then finally, I have an array of integers, and then there is a method called sum. There's a whole bunch of methods to do the kinds of things that you normally want to do with a collection of numbers. You can sum, you can average, you can max, and you can min. All of that stuff that you learn to do by hand is not really necessary anymore. Now, that all sounds great, but that's not how I came up with this. So now I want to show you the other thing that's awfully nice about Scala, and that's the REPL. So I type Scala. Scala is a compiled language, just like Java. So normally, when you have a bigger program, you compile it, you run it, just like you would a Java or C++ program. But in addition to that, it has this nifty kind of workbench that's built in, so which works more like what you might have seen if you've done some programming in an interpreted language like JavaScript or Scheme maybe. So here when I type 6 times 7, then it gives me the answer, which naturally is what it always is. So, and now I can also do some more programming in it. So let me read this file here. I have to import a couple of packages. So it's Java IO and Scala IO. Now I do it again. I just hit the up arrow key and it gets it back, so no harm done. So now it's read in this as an array of strings, each of the strings in my file. Now if I just wanted to know what the first one was, I could just ask it. Remember, you use round parentheses. And here's my first element in it. Well, that's not what I wanted to do. Now I wanted to hit this thing with, the splitter. So I say res2. It saves everything in a variable that it calls res1, res2, res3. First result, second result, third result, and so on. So I don't have to actually store it. I can just use those things. So now I say res2.map. And now what did I want to? Oh, I wanted to split. So I think I'm good by just splitting by by a single space. And now I'll get an array of arrays. Well, that's just way too scary, but let's just look at what one of them is. The first one, because I'm doing res2 and I need to look at res4. So the first one is an array that contains Bakersfield, Horace, whatever, the name. And here, this is the one that I want. So let me actually get this one. So what I want is res4 0. Oh goodness. Res4 length. Oh, of 0 length. -3. So that's the one that I want. But now I want to do it for all of them. So what I really want is I want to say res4.map. And now do this operation, namely get the thing, and out of that get and now I have my array of, it's still an array of strings, as you can see over here, but it has all of the salaries in there. So now I'm getting very close. So this is now res8. So now for each of these, I want to replace everything that's not a digit with nothing. Here it is. And now these are all integers. No, they're not. They're still strings. That's okay. Now they're all integers. Notice it's now an array of ints. And res10.sum. Here's the sum. So altogether, State of California pays $6.75 million to for these clowns, and that's not even counting the car allowance. All right, so that's how it goes. So the point of this is that when I discovered what I wrote down on this slide, I actually discovered it by being on the keyboard and making a few mistakes that I did not show you in the interest of time. And so it's a very easy and fluid way of working with the data set. You just load the data set into Scala, and you just massage it one step at a time, getting closer and closer to a goal, and eventually you actually have what you have. It's a huge difference between doing that and between what my poor freshmen had to do when they had to write a Java program, and they had to figure out everything before, because when it didn't work, what happened with the Java program? It didn't kind of give you an approximate answer, or it didn't show you something that almost looked like the real thing. It just didn't work. It said, you're stupid. You're stupid. And they tried something else. You're stupid again. And so freshmen hate that. And, the truth hurts. And so, with this kind of environment, you get encouraging and positive feedback. And that's just how any of these interpreted systems work. They let you, work closer and closer to a goal, and you can feel that you're getting closer. Yes?
Hi, is it writing it to a file, compiling it, and then executing it?
It actually is doing that, but you don't have to worry about it. So behind the scenes, it collects all of the input that you make, and when you hit enter, it actually very quickly compiles it.
Who's in my programming languages this semester? These guys all built that last project.
All right. Yes.
We did that for Java.
Yes, and you kind of want it for Java.
Tough now, right?
Yeah.
All right.
So now you know what actually goes on behind one of these things, and that's what it is. So you have the advantage of having the compilation that you need for the heavy metal, but you also have this this interactive system. It's very nice. So if your data is in XML, and maybe I'm not actually going to demo it because you may not need to know it right now, but there will be a day when you have a big honking XML file and you need to massage it in some way. It happens to everyone. So one day when this happens, then just remember Scala. So Scala has XML built in, and so you can actually just type a thing like this here. I'll just prove it by pasting it into the REPL. And so here there's a bunch of XML, and it's just an XML element in Scala. You can manipulate it. So I can, for example, find out what is the author in it by using this operator, if you happen to know XPath, you'll notice exactly like the // and XPath, except for obvious reasons they couldn't have used that one in Scala. As an example, one day I had to move a bunch of HTML files and I write them in XHTML that had images in them. I had to move them from one directory to another, and so I had to find all of the images that were in there. Well, what's an image? You know what's an image is. IMG, source equals, then whatever, quoted string. So you would have to find all of the contents of the quoted strings inside an SRC, inside an IMG. So what's the first thing that everyone tries? The first thing is, of course, regular expressions. Well, as Jamie Zawinski said, many programmers, when faced with a problem, think, oh, I know, I'll use regular expressions. Now they have two problems. So regular expressions are great, but when something gets a little bit more complex, then they very quickly break down. So I actually wrote it at the time in XSLT, and I hope never again to relive that experience. So I had to put in stuff like this into my script, and that didn't do anything at all. That just kept some recursion going that I didn't understand in the first place. But in Scala, it was a two-line thing. I snarfed up my document. I said, find me all of the IMGs, and then find me all of the source attributes, and that was it. 2 lines. So how did I find those 2 lines? By futzing around for 10 minutes with a REPL. So I tried a couple of things, and then it worked, and then I just wrote my script, and I was done. Images. For a textbook, I had to write a whole bunch of images of red-black trees, and a couple of hundred, actually. So this is not something where you go into Adobe Illustrator and say, oh, I'm just going to get busy and draw a couple of hundred images in Adobe Illustrator. For those things, you want to write a program that writes these images. And so there are various ways if you can do that. But to give you a slightly easier example, let's say for whatever reason you are asked to do some physical simulation. And here I came up with the simplest thing that kind of works. If you have a spring, it's a thing like that, and you displace it a little bit, you pull on it, and then you let go. You know how the spring goes up and down like that. And it's easy enough to model. There's a thing called Hooke's law that says that the displacement is minus kx, where x is the distance and k is some constant. And then there's Newton's law that says that the force is also the mass times the acceleration. And if you crunch the numbers, you get the acceleration out of that. And so now you have a velocity, and you update it a little bit. You update the position by that. And if you do that a few million times, then you get the positions kind of like that. But you don't see them. You print them out, and they're boring. So you want to actually physically see them. You want to see a little animation that shows them all. So basically, you have these 3 lines of stuff, and I assure you they do produce a you'll see it in a minute, a pretty good approximation of the motion. So what do people do? Well, when I ask people what they do, is they say, oh, I use processing. Did anyone ever use processing? All the graphics people use processing. It's a programming language that has been optimized to do animations, to do kind of fancy graphics and stuff. It has an API. It lets you do, let's just say, set the frame rate of something, so draw a line from here to here, put an image there, move things around and stuff. And that's the crazy part. It was written in Java, but you can't write it in Java. You have to learn another programming language. Another programming language that was invented by the cousin of the fellow who invented PHP, judging from the quality of both of them. So, I mean, the sad truth is that there's so many programming languages out there that are wretchedly, wretchedly bad. You think C was poorly designed, but C is actually pretty good. It's not like, Pascal or Algo or or Haskell or something, but there are many, many brain-dead languages out there, and processing is none too great. So you have to learn a new way of doing arrays and strings and functions and methods, and all in a kind of a half-baked way. And so I didn't want to have anything to do with it. Now, some smart fellow took the processing library and adapted it to Scala, so I can call it from Scala. So here's basically my processing program. So I can use the API, things like size and frame rate and rect. I can use those using the processing style. So I just looked up at the processing manual how to do that. But here I had to write a function. And that function I can use Scala. I don't have to learn a new language. So let me actually run you this thing. So it runs here, and it shows, with a few lines of code, the spiral moving up and down. Well, of course, that's not what we want. What you really want is you want to draw it as a spiral. Well, that's an exercise to the reader. And now that, if you think about it, you can do this in Scala by just figuring out how to draw a line segment and then, do a little bit of zigzag back and forth. You could do this with the material that I've given you on the slide, and then you would learn a language that's useful for 1,000 other things. On the other hand, if you do this in processing, you're going to learn a language that's useless for 1,000 other things. And so that doesn't seem to be like a great investment in time. So that's where the scalability of Scala comes in, that the same language, the same syntax, the same kind of rote memorization that you have to do to learn any language, that you don't have to do it over and over again. Okay, just a couple more things that are actually kind of nice. And that might make you think a little bit about other languages, actually. So as a Java programmer, particularly as a server-side programmer, I often have to write these classes that mimic what goes on in the database. I have a person object in the database. A person has a name and an age, just simplifying greatly here. And of course, really, the kind of things that I have in a database, I might have an address that has that has 10 properties, a zip code and street name and whatever. And so when I write the Java class for that, I fill in the fields, and then I use Eclipse and hit Control Space to get all the getters and setters automatically. And then I have this much class for this much information. And I have to, it's not that big a deal to write it, but you only write code once. You read it many, many times. Every time I have to go back and read it, I have to see, are these really just harmless getters and setters, or is there something interesting going on? And that's boring, and it's not very productive. So in Scala, you don't do that. In Scala, when you have something that you call a val or a var, then it automatically generates the getters and setters. For a val, only the getter. For a var, both the getter and the setter. So here I can make call the constructor, and they have this compact notation for the constructor too that one gets used to, but that's not the point I'm trying to make. The point I'm trying to make is you said var age int, and then you can say fred.age equals 42. But isn't that terrible? This is really, really terrible. Now I've broken the encapsulation. Anyone can now edit the private parts of my data. If everyone did that, the world would come to an end. Right? That's what we've learned in object-oriented programming. You must protect, you must encapsulate, you must hide the implementation. Well, that's actually true. And I'm not arguing against that. You should not automatically make everything visible. But when I look at the classes that are out there in the wild, there are an awful lot of classes that have get set for a whole bunch of properties. Not for every property, but for a bunch of properties. And so I put it to you that it's really no worse to do this than to have getters and setters. Now, you could argue getters and setters are not appropriate for everything, and you're right. Getters and setters have their role. Sometimes they're good, sometimes they're bad. But so the question is not public data, but getters and setters. So what Scala lets you do is they let you start out the class with this very compact shortcut for getters and setters. But if later you change your mind and say, oh, maybe my getters and setters, which now are part of the public API, just as if you had called them get and set, you can still change what that API does. So, for example, I could make it so that the setter can never make someone younger, which seems like a reasonable thing to do. And I do that over here. The setter has a slightly cryptic name, age_equal. And so here I'm making it so that the setter checks that the new age is bigger than the internal thing. Notice, by the way, here I do have a private variable with now a public getter and a public setter, where the public setter does something non-trivial. Now, in that evolution, the interface to the user of the class has not changed. So this is nice. You can start out simple, and then as you want to build in protections, if in case fact you do, 95% of the time when you look at actual code, you don't, but sometimes you do, then you have that evolutionary potential. So, in most of the times, Scala classes look at, have the, just in terms of size, are about a third to a fourth of the Java classes, just because you don't have all of that boilerplate. Java has interfaces, And interfaces are kind of nice, except look at a typical interface. I've just taken, because I thought maybe you're familiar with it, the mouse listener interface in Java. In Java, if you want to listen to to mouse clicks, you have to implement the mouse listener interface. It has methods for, has the mouse been clicked? Has it been pressed? Has it been released? Does it have a bad day? So for every one of those, you have to provide an implementation. Most of the times, you only care about, has the mouse button been clicked or pressed or something, and the other ones you don't even care about. But in an interface, you can't have implementation in Java. In Scala, you can. So in Scala, it's not called an interface, but a trait, just to have a slightly different name. Just like in Java, a class can implement any number of traits, and those traits can have behavior. So here, for example, the mouse released method by default can do nothing. You can override it if you want to do something. The mouse clicked method can reference an instance variable. So traits can have variables even. And again, you can have as many as you like. So you pretty much have to have multiple inheritance, but not quite. So it avoids having to have an interface and then an abstract base class like you have in Java. And in Java, that pattern doesn't really work so well because you can only have one superclass. And what if you wanted to mix in two kinds of behavior and both of them have some default? So it's a very nice touch that people go to town with. There's a third kind of classes that are interesting called case classes. A case class is optimized for pattern matching. Sometimes you have very simple kind of data structures. So for example, think of modeling tree nodes. You know, what's a node in a binary tree? It has a value that you store in the node. It has a left subtree and it has a right subtree, which by default would say are empty. And now we can say a tree is either an empty tree, which is even simpler, it has nothing in it, or it's a node with some that stores some value. And benefit number one of using case classes, you don't have to say new. Doesn't actually sound like a big deal. I mean, when's the last time you cried when you had to write new? But when you make a deeply nested structure, it is kind of nice to drop the news. Here, for example, I'm making a tree, and you see it's kind of readable. It's this kind of tree over here with a bunch of nodes and empty constructors. And if I were to put new in there, believe me, it gets more cluttered up. I do this stuff all the time in my little graphics library, the one that draws those the diagrams, of which I need to have hundreds, and it does make the code easy to read. But that's not the main thing. The main thing is you can use it for pattern matching. So pattern matching looks kind of more or less like a case statement in C++ or Java, but it's a case statement on steroids. I'll just show you an example. It's easier to see that. So let's say I have my tree, and now I want to sum up all of the values that are in the tree. Now imagine how you would do this in Java. In Java, you would have to write this recursive function. Right? It goes to the root, and then goes to the left and the right. And here it's a bit simpler. I say, take my tree node, and now make a match on it. And there are two possible cases. It could be a node, and that node has to have some value, some left, some right, and so you can give them names like this. And then you can use those names in the description. So here I say, well, I take v and I add what's in the left and the right. So it's a recursive function. And if it's an empty node, then my sum is 0. So that's my function, and it's short and sweet. So who needs it? So I want to just show a little bit. If you remember when you had your data structures class, that's what I'm teaching this semester. And I haven't even gotten to trees, but I can already smell the fear of my students when they need to manipulate them. I mean, everyone intensely dislikes trees. Remember when you had to code up removal from a binary tree? And how it was just a pain in the neck. In this kind of functional or more algebraic setting, it becomes actually very easy. I won't show you removal because it takes about twice as much space, but I'll show you insertion, which is like totally easy. And then it has a twist that I want to talk about. So here I have my my tree classes before. And now I want to define an insert method. So I have to define it in the superclass. Then I have to define it for both empty trees and for non-empty trees. So how does it work? When you look at a textbook, it says to insert something in an empty tree, you make a root that contains the thing. That's this case here. Inserting in an empty tree makes a root node. To insert into a non-empty tree, well, you have to recursively insert either in the left or in the right subtree, depending on whether the thing that you want to insert is less or greater than the thing that you find. So here it is. If it's greater, Then you make a new node into which you copy the original value. The left you leave alone, and you recursively call insert on the right. Otherwise, you do the opposite. And finally, if v equals the value, then you just return yourself because the tree has not changed. Notice that this insertion function is a little different from the one that you have seen in your CS2. It does not modify the tree. It returns a new tree, a brand new tree, never before seen by anyone, that now has your thing inserted. So for example, over here, I start with the empty tree. I insert 3, gives me a new tree containing the 3. I insert 1. I now get a new tree containing the 1 in addition to the 3. Another new one, another new one, another new one. So these things are immutable data structures. You don't modify them. You always operate on them, and you get a new one. Who needs them? The reason you want them is they're safe for concurrency. So it's, when you write a concurrent application where multiple threads operate on the same data structure, you have to protect that data structure like crazy because they're sensitive little creatures, and you have to make sure that only one thread operates on them at any one time. On the other hand, if you have something that's immutable, these are perfectly safe. It doesn't matter. All sorts of threads can look at them at the same time because they can never be changed. If one of them wants to change them, well, then they say, make this change and give me the result. It doesn't affect the original, and then that other thread can do with the result whatever it wants to do with it. It makes for writing concurrent programs, correct concurrent programs, much simpler. So there's a whole bunch of these immutable data structures. Now you might say, but isn't that incredibly costly? I have this big tree, contains 1 million elements, say, and now I'm inserting one element. Doesn't it have to copy 1 million elements? But if you think about it, it doesn't, because all it has to copy is, imagine where that new element ends up. It ends up on some path, and that path indeed does have to be copied. The rest, if you look at what it does, it builds references to the existing tree into the new tree. So let's see how long that path is. It would be log of 1 million, log 2 of 1 million. That's about 20. So yes, you do have to reroute about 20 of the elements, but the other 980, they stay the same. So it's not actually very inefficient. You have structural sharing between the old and the new for the bulk of the material. And now, admittedly, a lame binary tree isn't very effective, but people have been doing these immutable data structures that are very efficient, and they have implementations in the Scala library. So the advantage of looking at something like this way is, for one thing, it makes standard algorithms simpler to represent, and it also gives you this benefit of immutability that's getting ever more important as we look at concurrent programming. So, in fact, concurrent programming is on the minds of everyone these days. You don't remember this because you're young, but I do. When I first got into this business and I bought my first portable computer, there was a Compaq Portable, as it was called. It was about twice as big as this briefcase. It had a nice leather handle. It weighed like 30 pounds or so. And it was obsolete after 3 years, of course, because the new machine that I could buy for about the same money was like 4 times as powerful or something. So I ditched it. And like clockwork, every couple of years I would buy a new laptop because it was worth the money. I was in the business, and what's a few $1,000s if that's your livelihood? And every couple of years I would throw the old one away and get a new one. But it's gotten less and less fun. So now when I tell my wife, well, of course I need a new laptop, it's been 2 years. And then I get the new laptop and I turn it on. It's really not any faster. I mean, maybe a little bit faster. It looks nicer, right? But so they have stopped getting faster. Instead it has 4 cores. What am I going to do with 4 cores? I only have one brain. So so that's the problem nowadays, that the laptops, they scale out. They don't no longer increase in clock speed. So your programs have to start taking advantages of these cores. Now, why don't we just all write concurrent programs? Have you tried it? Is there a concurrent programming class here? Or?
Yeah.
Okay. So, I mean, when you try it, you realize that it's hard. It's very, very hard to write correct concurrent programs. It's very easy to write programs that are concurrent. but they often do strange things. So, so there's all these different approaches in the world on how one can deal with that, and one of them is the so-called actor model that was popularized by the Erlang programming language invented by Ericsson. So Ericsson makes these phone switches where there's millions of phone conversations going through one of these switches at any one time. And Erlang is actually kind of interesting in that it's not just a language, it's kind of its own little operating system. You can update code on the fly because you can't reboot a phone switch ever. So when the phone switch needs some kind of tweak in the software, you have to kind of put it on it while it's still connecting all these other phone calls. And so Erlang has been optimized for this particular problem domain. It's a little bit of an oddball language, very strange syntax and stuff, but it does have this one very interesting idea of these actors. So an actor is this autonomous agent that does some kind of calculation, and what makes an actor tick is it never shares data with anyone, because sharing data is what kills you in a concurrent program. If you have two threads concurrently access the same data structure, then one of them can make some update that the other one isn't aware of, and you can you can corrupt your data structure very simply. If you have no sharing, you don't have any of these synchronization issues. So actors do that. They live their own existence. They work on their own little data items. Then when they're done with some computation, they send that data to another actor, having relinquished ownership thereof. Then the other actor gets to own it. And so no data item is ever owned by two actors at the same time. The other thing is that when you contact another actor, you just tell them, here's stuff, and then you move on with your life. You don't wait for the other actor to come back and say thank you. Or if it wants to say thank you, then it'll happen asynchronously. So much later, you might get a message in your inbox that says, oh, Joe said thank you. And so the advantage of that is that you don't block, because the other evil thing about concurrent programming is if you structure your program so that you say, I'm going to wait for this action to be completed, then it can easily happen that someone else says, I'm going to wait for your action to be completed, and you wait for each other. Or more often it happens in a circular fashion, that a long chain of actions try to wait for each other. So I think I'll skip the syntax and the example here because it's a little technical, but what Scala did is they said, this is a great feature. And some people will be intensely interested in this. But right now, if they wanted to do that, they'd have to learn Erlang. It's a new language with a strange syntax and its own operating system. And that doesn't make any sense. You want to have a library. But you still want to have syntax that's reasonably reminiscent of something that these other actor systems do. So, for example, in Erlang, you use the exclamation mark to send a message. And you can do the exact same thing in Scala. So in Scala, you can define operators to be methods. And so you can say my actor message, and then it looks familiar to someone who knows this kind of problem domain. So they did that. They implemented the essence of Erlang actors inside Scala. Now you have a programming language that, admittedly you have to learn one, but you only have to learn one, and that also gives you actors. These are incredibly popular for the kind of back-end applications for which they work well. Now, in fact, they're so popular that there's some people who say, you've got to learn Scala because then you've mastered the actor model and all your concurrency woes are over. And I did want to not have people fall into that trap, because it's just not true. Actors are great when actors are what you want. So if you have a very distributed system, then that's with a lot of loose coupling, actors can be quite wonderful. If, on the other hand, the computation that I have the code example for, that code goes through a file system, goes through all of the Java source files in a file system, and extracts keywords out of those source files to find out which ones occur most frequently. And that one turns out not to be such a great match for actors, actually, because you have these independent agents, and they do their computation, and you somehow have to direct that computation. For example, when you search a whole bunch of files and you give statistics to some accumulating actor that then summarizes the results, how does the accumulating actor know when it's done? That's a common problem in an actor-based system, that at some point you want to be done and you want to have a result. The way I solved it in my sample application is I had another actor that just counted all of the files, reported back to the summarizer, say, if you've gotten this many messages, you will be done. And that kind of works, but it took a bit of time to think about that solution. So using actors doesn't always map to the kind of problem domain that you have. Particularly if you have heavy concurrency where you have, where you want to do, for example, doing graphics processing or doing computationally intensive stuff that keeps processor busy all the time, actors tend not to work all that well for. So also in Scala, unfortunately, you can make mistakes in actor programming. In Erlang, you can never have actors share mutable state. But in Scala, it can happen by accident. And they're working on some, on cranking up warnings for that. But it's an issue that when you take the good parts of one language into another, that you sometimes have these mismatches. So actors are great, and I don't want to say that they aren't, but if someone says, we've got to use Scala because we've got to solve the concurrency problem and Scala has actors, that's a little bit short-sighted. What Scala really has is it's a good host for a whole bunch of different concurrency solutions because there's no one silver bullet when it comes to concurrency. So here's what I think is a much, much niftier feature, at least for the kind of stuff that I do. I often do computationally intensive thing that's on a single processor. So for example, I wanted to compute, for whatever reason, I have some large data set, large array, 1 million elements, and I want to do some kind of computation. Say I want to compute the sum of all of these elements. I have 4 cores. So if I have 1 million elements, I could have one core, adds up the first 250,000, the next one, the next 250,000, 250, 250. They're all done. They report their sum. I add up the 4 sums, and I'm done. I can program that in Java. There's actually a nifty thing called the fork join framework that lets me do that in Java. 150 lines of code. I can program this in Scala. In Scala, I say, give me my array and compute the sum, but I put in this little dot par. And that parallelizes the computation. So the Scala library has this parallel collections that say, when you make a collection parallel and then invoke a method on it, then that method automatically gets distributed over the number of cores that you have available on your machine. 4 keystrokes, and I'm a genius. It's correct. It's fast. It really is faster. And so that's the kind of power that a language can give you that has a whole bunch of buttons under the hood that you don't normally see that enables some very smart people to make these kinds of things. In Java, you could never do this. It would simply not be possible in Java to take the Java collection library and make it so that some very smart fellow could do the dot par and then parallelize the entire Java collection library. In Scala, they've done it. So if you need to do that kind of computation where you just need to quickly do stuff on the same data structures, Scala has you covered. So, so kind of the pitch for Scala is that there's lots of things that anyone wants to do, and there's lots of special purpose languages for every one of those things. Erlang does this parallelism. Processing does the drawing and the animation. And at some point, it's too much. Every time you learn a new language, you have to learn how do arrays work, how do methods work. And it takes a while for your fingers to get used to this thing and to type these things fast. And it's just a complete waste. I mean, I'm right now dealing with projects where I have to do an itty-bitty piece in JavaScript and something in Java, and then the build automation is in Ant, and there's like 6 languages in this project. That means to do looping, I have to figure out how to do this in 6 different ways, and it does slow people down. And so what the Scala guy said, what does it take to have a language that is that scales, that is good for small things and that's good for large things? And you asked why was I interested in learning Scala? And I'm interested in learning Scala because I'm lazy. I do not want to learn 6 more languages. I'm also old. Did I mention that? So So the promise of Scala is that it's one language, and you learn it. And every language is tricky to learn. It took me several months to get to a point where I felt fluent in Scala. Which I think is par for the course. That people say that if you learn a new programming language, after a few months you kind of start feeling at home, and after a couple of years you become so fluent that it becomes second nature. You can't expect to learn a new language in 3 weeks. It's better than with natural languages. I've been trying to learn French for ages, and let's say you're enticed by this and you want to get started. So that TypeSafe company liked the book that I wrote, that Scala for the Impatient book, so much. They said, can we distribute the first so many chapters for free? And I said, well, yeah, free, huh? Sure. So so you can go there and get the first so many chapters, and that's great to get you going. It assumes that you know Java or C++. It doesn't teach you anything about here's what a loop is, here's what a variable is. It just says, here's how you do it in Scala, blam, 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 one fact after another. So the Scala compiler is a free download, works with any text editor, and I recommend that if you wanted to try this out, just try it out in its most basic form. That's kind of what you've seen me do today, because the IDEs get in the way for learning. Use the REPL, that interface with that quick feedback for learning it. And what I did is, at one point I said, I've got to learn Scala. Every silly little thing that I need to do for day-to-day automation, of which I have a project a week, I'm just going to do it in Scala. Like that thing that extracted all of the image names from an HTML file. Or I had to do something that takes a bunch of student files and rearranges them in a certain way. I said, no, I'm not going to use shell, I'm just going to do it in Scala. And after a few weeks of that, I was able to do basic things in Scala pretty quickly. You don't have to force yourself to do it. The most important thing is Scala is a large language because it has all of these things that I didn't show you, how to build these libraries. Now, maybe you don't actually want to build a new library. Most people don't really want to build a library. And so there's no sense in trying to understand the whole language. No one does. Even the creator of it, I think at this point, will cheerfully admit that there are parts of the language that are pretty mystifying to him. So it's an easy language to get you to a point of very of efficiency and competence. Now at some point you'll want an IDE, and nowadays you can get Scala plugins for the most common IDEs: Eclipse, NetBeans, and IntelliJ. Right now they're in this process where they kind of leapfrog each other in terms of quality. The Eclipse plugin seems a good start. And then there's this nifty system that if you want to play around with, called Kojo, that I'm going to give you a link for. And Kojo is Scala for junior high school kids. So this fellow has done a turtle environment where you move a turtle and it draws stuff, and it does draw some math pictures that shows you how a circle can make a sine wave and stuff like that. And the language that is driving it is Scala. And so the kids only, of course, see a small subset of Scala, but that fellow said, why should one learn another language? Here's a perfectly good language that has decent syntax, and I'm just going to use it. And so it's some fellow somewhere in India. No one knew about him, and all of a sudden this beautiful environment appeared, and there it was. And it's actually a very nice environment to get your feet wet with Scala. So to conclude, how do we get there? So really, what made Scala interesting is that people are generally unhappy with the state of particularly server-side Java. There's this article that came out a few years ago by Bruce Tate with the great title, Don't Make Me Eat Elephant Again, where he described how it was such a horrible thing to have these very lumbering, cumbersome Java libraries, the XML configuration and stuff. And so at first it looked like Ruby and Rails were the salvation, because lots of people said, oh, this is much simpler. You can bang out a Rails app very quickly, and yeah, you have to learn some Ruby on the way. But so what? Ruby is a pretty nice language. But apparently Ruby is not so nice that anyone has used it for anything else. So if Ruby was really that language that was so powerful that we can use it for absolutely everything, we would be seeing a ton of other Ruby libraries, and we aren't. So apparently that's been a bit of a dead end. We don't want to have a separate language for every problem domain. And the latest fad, of course, is that everything is in JavaScript, right? Node.js, you write your server in JavaScript. I mean, which part of this is not crazy? I mean, there are parts of the Node.js architecture that are very good. The Node part is good. The .js part is the problem. So, so the trend is towards languages that are more expressive, that have fancy constructs built in, that have less boilerplate. And so Scala is right now the best thing out there. And will it be the one that everyone gravitates to? Maybe. If it succeeds in industry, and that would mean if there are large numbers of applications and application frameworks that use Scala, then people will learn it just in order to partake in that ecosystem. If someone comes up with slicing away some of the complexity that you have with any large system and makes more student-friendly subsets, like the fellow who did Kojo for middle schoolers, if someone did this maybe for college students or for beginning programmers, then it might kind of grow bottom up in a way like Java has. And so there is a possibility that it will. But of all of the languages that are out there, if I didn't already know Scala, it would be the next one that I would want to learn. And so maybe so do you. Thank you. Yes, a bit of time for questions.
What's the state of debugging? Has it gotten better with the correlation between the debugging and the source code?
It's a work in progress.
I had to hit you with that, huh?
No, but it's. But how's JavaScript debugging working out for you?
Not.
So it's true that the Java tools are marvelous, right? That the quality of tools in Java is like better than anything that anyone sees anywhere. And I think it would take a sustained effort to do that in Scala. And in fact, the IntelliJ people who have a pretty good Scala support are unhappy about some features of the language. And that's why now they want to come up with their own language that they think might be a better match to an IDE.
I sent them a 5-page description of what I was dissatisfied with their new language.
See, they're not language designers.
Yeah.
They're IDE designers. Yeah, it's so. Other questions? Yeah.
Say versus a language like Python, where would it be an example?
Oh, I see. That's a good question, because Python is a pretty nice language, right? And but Python is not really good enough for building tools that mold Python into something more powerful. So could you have written Rails in Python, for example? I don't think you could. I think there's not enough meta stuff in Python to do that. And people have written some web frameworks in Python, but they've not taken on like Rails because they didn't have that kind of ease of use or the fact to reflectively model the database or something like that. And so I used to want to learn Python to do the small stuff. But I'm kind of glad that I've learned Scala, because in Scala I can do the small stuff and the big stuff. So yes, I do know enough Python to be dangerous, but I've never been really that interested in getting to be a hyper-efficient Python programmer, just because it only goes so far, and why do that when I can go so far? Yeah?
Can you throw this on a Tomcat server?
Yeah.
So you can do any...
Oh, you can do all sorts of web stuff. I mean, in this day and age, lazy people like me don't just do Tomcat. I just do the Java EE stuff. It works fine. So I just say, I can't figure out databases. I just use JPA, and and with Scala, in fact, I write my server-side code in Scala just so that it gets shorter. That I don't have to write the getters and setters. They're not much of a great excuse, maybe, but I just have small and medium-sized projects. Yeah, they work just fine. You have to add some humongous jar into your war, but so on. Yeah.
Are you teaching a freshman class, an intro class in Scala?
Oh, no. I wouldn't do that without better tools. I mean, it's just like if you teach a freshman. Did you ever teach a C++ to a freshman? You know how it is that but yeah, that's what I thought when I was taught C++ to freshmen. And then they would come and say, "What's this error message?" And somewhere, they transpose 2 tokens or something, and which caused the C++ compiler to tell you its life story. And and then the student asks, "Why did it do that?" And then you scratch your head for 20 minutes and say, "Oh yeah, that's maybe you figure out." But in Scala, it's the same thing. That because it's a rich language, So what one would need is something in Scala where the compiler will enforce a subset. And you have that like in some scheme environments. They have that like in Racket. You can say, I only want the beginner subset. And that would be a marvelous addition to Scala. And I know some people are interested in doing that. And if something like that were to happen. And actually, if you were to ever design the next big language, if Scala doesn't succeed, thinking in terms of these subsets would be a really good way of approaching it. Scala has these informal subsets, the beginner, intermediate, advanced kind of levels for application developers and for library designers, but they're not enforced. And enforcing them would be great, because then there would be a way for a student to get in there. But I might at some point give it. No, I don't think I would. So that's one advantage, in fact, of Java is that Java is relatively simple. But even for freshmen, I don't know. I just came back from SIGSI, and we had all this discussion on should one really still teach freshmen in Java in this day and age, or should one let them use like a block-like language where they can't make any syntax errors, and then once they've learned to program, transition them to syntax. And I'm somewhat sympathetic to that point of view. Other questions?
Well, thank you for coming.
Well, thanks for having me.